I have shown this graph before. I have oscillators with performance that compares nicely with the Citrine from Wenzel. So this might look impressive, but the Wenzel operates on 100 MHz and my oscillators are on 10 MHz. So ideally I would like to see a 20 dB difference. But that's not what I do. The difference is maybe 6 decibels at best as a separation of 1 kilohertz. Now the plot here is the sum of the AM noise and the phase noise from 2 oscillators. So actually the phase noise from 1 oscillator should be 6 decibels below, means here, but there is still some desired improvement. So this video is about what is the reason for this noise that I see and can I do something about it. To that end I have this set up. Starting with an oscillator running at 30 dBm plus 30 dBm output. It's followed by an attenuator that I can set from 0 up to, let's say, 60 decibels or so. Followed by a hybrid that splits the signal in 2 equal parts. So this is the interferometer from here up to the next hybrid where the signals are combined again. So one leg goes through an attenuator, followed by the amplifier that I want to investigate. This is the same design as I have as the oscillator, but here the limited output is not routed to the input, it's left open, and I can measure the noise on the limited output later. Then there is a 3 dB attenuator, because this one brings a lot of signal and also a noise floor that is a little bit higher than I need to be able to measure it. The presence of this attenuator makes the impedance looking this way more close to 50 ohms. And in the other leg I have an adjustment for phase and amplitude with a couple of boxes, followed by a coupler where I can send in a signal from a signal generator, and the second coupler where I can take out the signals coming through here. And then there is this hybrid that combines the signals, and the sum is followed by a impedance match box by which I can set the impedance equal for the sum and the difference outputs in order to isolate the 2 legs from each other. I don't know if that is really necessary, but it's nice to know that signal doesn't go this way. The difference output is ideally 0, and that's where I measure the noise. It has first an impedance match, followed by an attenuator, which is normally 0 attenuation, but I can switch in attenuation here. And it is important that the low noise amplifier here looks into the same impedance always, regardless of the setting of this attenuator. So this impedance match is adjusted to make the impedance seen by this LNA always the same. And that is in order to make sure that the noise figure of this amplifier doesn't change when I change the attenuation. And then there is an impedance match again. This impedance match makes sure that the impedance I see looking this way is always the same. And then the difference signal is analyzed by a low noise amplifier, followed by a low pass filter at 30 MHz, because there is some 20 MHz presence, even though this bandpass filter suppresses fairly well, still the gain is very high of this LNA followed by that. So to not have too much on 20 megahertz, there is this low pass filter and then another amplifier and a hybrid that splits the signal in equal parts. Half of it goes into the Perseus, the other half into an oscilloscope, the channel 1. And that's the oscilloscope that looks at the sum signal from up here, which is triggered by the sum signal, which is a good measure of the phase of the sum signal. Step 1 of the setup procedure is to look with the network analyzer into the attenuator and adjust the impedance match here for the impedance that I see to be the same when the attenuation is 0 as it is when it is high. At a high attenuation I see accurately 50 ohms, but when I have 0 attenuation I need some adjustment here because what I see here comes through the hybrid and reflects the impedances on the input side of the hybrid. And here you can see very close to 50 ohms. I have now 40 decibels of attenuation. Now attenuation is 0. And you can see the marker is at 50 ohms here. And the frequency is 10.0 megahertz. I have adjusted that impedance match box a little bit to achieve this result. The second step is to connect the network analyzer at the attenuator input and to set this impedance match for the impedance to be 50 ohms also when the attenuation is set to 0. This amplifier has noiseless feedback with transformers, so the load is reflected back to the input. And by setting the impedance here constant, it means that the impedance seen at the output of the hybrid is also constant. What I see might not look so good. You can see here is the marker and here is 50 ohms. But there is a problem. The power level here is 0 dBm. That's a lot of power. I make it minus 50. And now it's a bit noisy, but it's at the right place. And I make it minus 40. And there is a small difference, minus 60. But this is close enough. The third adjustment is not for impedance, it's for signal level. I disconnect this and connect the spectrum analyzer at the hybrid input. Means I'm sending signal this way. It splits here, and if these impedances are not the same, I will get a reflected output here. So I use this impedance match here to set a low level at the input, this input of the hybrid. So these are the 3 adjustments I have to do at these points. When doing the third step, means checking the balance in the hybrid, it's necessary to make sure that this LNA is not saturated. There are 2 ways to do that. I can set this attenuation high, or I can set this attenuation high, or both. But I must keep the signal that reaches this LNA low, and I can check that by looking at the Perseus or the oscilloscope, where I have the level in the difference channel. With the current settings, I read minus 70 dBm approximately. I disconnect one of the outputs from the hybrid, like that. And then I see minus 46. So this is better than a 20 dB suppression when both connectors are connected. I have stopped this oscillator by removing the feedback from the limited output to the input of this amplifier, which also is the oscillator. And I set the attenuator to 70 decibels. It means that what comes out here is just room temperature noise from the 50 ohm resistors in these attenuators. Then what comes into the interferometer, one leg here is the 50 ohm room temperature, and phase and these couplers doesn't matter. So here I have room temperature 50 ohms. In the other leg I have this attenuator and the selective amplifier, and it's followed by not 3 dB, I have to change that. It's actually 5 decibels of attenuation after the selective amplifier. So here I have the noise floor of the selective amplifier minus 5 dB at one input and room temperature 50 ohms at the other input. And the difference between them goes into the evaluation thing, into the pairs. And I will first just show what it looks like. What we can see here is there is a lot of noise at 10 megahertz. It's the thermal noise of the crystals plus the noise caused by the equivalent noise current of the JFET transistors. And it's something like 18 decibels above the flat noise floor. So what I will do as a first step is to establish what is the power level of this noise. I will do that with the noise figure meter. First I set the bandwidth to 100 Hz. I do that by editing the text file that you can see here, the RSSB underscore BG. There is a parameter here which is filter flat. This is half the bandwidth because the filter goes plus minus 50 Hertz now. I'm using this temperature limited diode noise source, and I've connected it here, which is 3 decibels plus 2 decibels and then into the hybrid. So I'm looking for the noise figure at this point, labeled 4 here. Find the noise figure at the output of the selective amplifier. The meter is now at 10 decibels. And I switch off this noise source and look at the S-meter graph of Linrad. With the noise source on, I had a level of minus 173.6. And I wait a little while. And then I read the noise floor here. It is minus 176.6. It means the difference is 3 decibels, so the noise figure is 10 decibels. A noise figure of 10 decibels here means the noise figure in here is 5 decibels, or in here it is 2 decibels. And the noise figure of the low noise amplifier is 1 decibel. So there is some loss in the bandpass filter and in the impedance match, but it is small. Knowing that the noise figure is 10 decibels, I know that the noise power is minus 164 dBm per hertz, which means I want the meter to show minus 144 dBm for the 100 hertz bandwidth that I have selected. So I have calibrated accordingly. When I connect the selective amplifier, this is what I see. It looks as before, and when I read out the noise floor, I find minus 125 dBm, or minus 145 dBm per hertz. So this is the noise floor at the close range, which is unavoidable. I can verify the calibration I did by use of the noise figure meter by sending a signal into here from a signal generator. So I have set minus 60 dBm on 10 megahertz. And this is what I see on the S-meter graph. And when I try to read it out, I see 60.2 dBm. So this works perfectly well, and both methods are equally accurate to within a few tenths of a decibel. I have disconnected here and placed the 50 ohm dummy load for this chain to look into. And now I will enable this oscillator. The filter is centered 200 Hz below where the carrier will come. And now I enable it. And it comes here. But the interesting thing is what happens to the noise floor. And here is the noise floor without the carrier. And I have to wait for a while for this was the point where I started it. You can see on the waterfall that the difference is very small. It looks like there is some little noise very close to the carrier. But 200 Hz away, I don't see any difference. And I will wait for this transient to move one further step and then read it out. So I read from here until here, and it says minus 128.72. I had minus 128.77. Now, a couple of hundredths of a decibel is not significant, I don't think. The carrier level, I can click on the carrier, and then I can read the carrier level, and I don't worry about the details. It's about minus 40 dBm. So it is 70 decibels below the full carrier at plus 30. So I go back to the offset here, 200 Hz away, and now I will enable the interferometer. That means disconnect the dummy load I have here and connect back to the hybrid. And then I can adjust phase and amplitude for these two signals to cancel, to get a very small carrier at the difference output. This does not make any difference on the noise floor, adding something that cancels the carrier. But you can see the carrier is much weaker, and I don't see the noise at the sides anymore. And I see the same noise floor. Now I can increase the carrier. So what I will do is to reduce the attenuation I have here in front of the interferometer. Currently I have an attenuation of 70 decibels. I reduce it to 50 decibels. And you see a transient when I did that. But the noise floor did not change, at least not much. I have to check the balancing a little bit. Like that. And then I add 20 more decibels. And again balancing. And now I can actually see some noise coming up here. A significant amount of noise. And I can also see the modulation sidebands from the amplifier. And a lot of noise close to the carrier. So this is sideband noise modulation caused by the selective amplifier. With 30 dB attenuation, I see minus 125.5. At 70 and 50, I was seeing 128.7. So it means that about 50% of the noise I have here comes from the wideband noise of the amplifier, and half of it is modulation by the amplifiers or something else. So I reduced by 10 dB. Now there is only 20 dB attenuation. And I have to fix the balancing here to not saturate the Perseus. Here I had a stability problem. I didn't bang the table or something, it just came like that. Probably a connector somewhere. You can see on the S-meter graph. So I will try to see where I have a poor connection. Now the attenuation is 10 dB only here, and I can see stability problems on the difference output, that is the input to the Perseus. And of course I see significantly more noise here, and the noise level changes as balancing degrades here, so I tune that better again. And then look for the noise floor here, and I will take a reading. And I can still see there is some kind of instability. This is not pure flicker noise, it's something else also. But I go for this a little lower value that I find occasionally, because the instabilities could be fixed. And now I read minus 109.8. Minus 109.8. So it's almost close, very close to 10 dB above the previous reading. And I will take the final one with 0 attenuation. The amplifier is not quite stable enough for this. So I have to retune all the time. And this is non-trivial because the amplitude adjustment is actually to a large extent relying on impedance mismatch losses. So the knobs behave a little bit peculiarly. Oops. Well, this is good enough. And it stays okay now. And it has stayed for long enough. So I read this. Minus 101.8. And this was all at a separation of 200 Hertz. I have swapped the selective amplifiers, means moving this unit here and give it feedback to become an oscillator, and moving this unit here and use it as an amplifier. I have measured at 200 Hertz, but also at 1 kilohertz. And the upper table was with one configuration, and the lower is with the amplifier and the oscillator exchanged. And the result looks very similar. You can see here 151 or 152. I have dBm and also dBc per hertz. Now, what I can see, going from 200 hertz to 1 kilohertz, that's a factor of 5, means 7 decibels. But the observed noise level differ by 20 dB or 19.2 dB respectively. That looks like 1 over frequency to the third, not like 1 over f as one expects for flicker noise. I don't know why this is, but that's an experimental observation. I can check calibration in an independent way, means send a signal from this signal generator into the interferometer with this coupler, and then pick up the carrier that is passing through, as well as that signal I injected, and I can set that injected signal to be 70 decibels below the carrier. And then the hybrid will cancel the carriers from the upper and the lower, but that injected signal will be unaffected. So here is the SDR IP, and I have set the carrier at 10 megahertz to show 0 on this scale. And then I go 1 kilohertz down to find this signal. Here it is. And it should be close to minus 70 because I set it there. As you can see, minus 70. And then I go to the Linrad screen here, and things look bad because balancing is not good enough. I have to do the balancing. And now this injected signal 70 dB down dominates. And then I look at the screen. Where is it? If I use this read out tool like that, oh, I have to wait a little bit more. Here, it says minus 40.7 dBm. Now the carrier is just at plus 30, which means we are 70 decibels below the carrier. This is a fair agreement with the calibration I did yesterday. And I haven't changed anything. So numbers seem to be correct. The entire system has been running untouched for 15 hours or something like that now, and stability is much better than it was yesterday. I think that has to do with the cables relaxing, because when I touch a cable like that, things change, and almost all the cables have the same kind of sensitivity. And this is plastic, polyethylene inside, and PVC and some copper surrounding. And it moves very slowly after having been touched. So part of the noise I see is due to the cables. That means noise very close to zero frequency separation. You can see it is far more stable than yesterday. But not fully stable, of course.